Hello, my name is Jose Martin Garcia, and I'm going to be talking about uncertainty, the representation and propagation. This is a new edition and very useful for representation of physical quantities and their errors.
Thank you for coming. Being a physicist myself, it is a great pleasure for me to introduce the concept of uncertainty in the Wolfram language. This is a concept of broad applicability in science and engineering, in research and industry. There are many reasons why, when we have measurements, there can be uncertainty related to incomplete definitions of what we are measuring, problems with sampling, repetition of observations. And so this has been a long-standing issue that, for example, in the Wolfram Alpha database, they have lots of data that needs representation with errors. So it will be great to have this new object. So historically, there has been always a variety of methods to deal with uncertainty. And fortunately, in the last few decades, there have been an effort to organize the various methods, and the various organizations of measurements of different countries have agreed on a document which is now very famous, called the GAM document. This is an abbreviation for Guide to the Expression of Uncertainty in Measurement. So our objective here is to do something which complies perfectly to what this document says. This document has been produced by this working group of metrology, and the current edition is of 2010, with minor corrections since then. It's based on a recommendation from 1980, and in fact, most of the main ideas, the names, etc., were already there in a one-page document from 1980. Quite interesting. The objectives are to promote full information on how uncertainty statements are arrived at, and to provide a basis for the international comparison of measurement results. In a sense, what the SI units did for the measurement itself, this document tries to do for the representation and treatment of uncertainty. So in this document, they start by trying to change some of the nomenclature, the traditional nomenclature. So for example, they insist that error is not the right concept, because error is the difference to the true value, and when you measure something, you don't know the true value. So we shouldn't talk about errors. This is more about data estimations, so the concept of uncertainty is more general. They give this definition here. Uncertainty of a measurement is the parameter associated with the result of a measurement that characterizes the dispersion of the values that could reasonably be attributed to the measurand. The measurand is the thing we are trying to measure. Uncertainty is a nice name. Then the traditional distinction between statistical errors and systematic errors is replaced by these new names, which are not so good, type A and type B. But this is what they suggested already in 1980, and this working group has kept those names, and now books use those names as well. However, this is about the origin of the uncertainty. In our representation, we will not care about where the uncertainty is coming from. We care about how to represent it and how to combine it, but not where it's coming from. So type A and type B is not going to be a concern for us. Then they have a new word for what is usually called propagation, and I still call propagation, which is combination. So what we called error propagation is now uncertainty combination. And then there is the concept of extended uncertainty, which I will mention in passing. It's when we express uncertainties with expressions like 3 sigma instead of the standard 1 sigma or 95 confidence level, this sort of thing. So it's just an alternative way of expressing the same uncertainty. Okay, so let's go for the main object being introduced here. This is this concept of around. So I have to start saying that this is all experimental design. It may change, and in particular, because Stephen is not very happy with the name around, this will probably change. So it's a very difficult. We have been considering lots and lots of names. So we would love to hear if you prefer some particular name or have suggestions. So okay, so the basic object is this one, around. And we have the value, the best value for a measurement, like say this one, and this is the uncertainty, right? So automatically it will be represented with a given number of significant digits. And we will talk about that in the next slide. But the important thing to realize is that internally it still has all the digits we entered, so that when we do computations, we are actually handling all the digits we have. It's just for type setting that we choose a particular number of digits. So now if we do a square root of that, for example, we will get the square root of that, and there will be the standard propagation or combination of error. And still we have all the digits inside. We can do this with symbolic input. So, well, perhaps I should evaluate some of this. I think I have this is in the prototype kernel so far, right? So, so we can do the combinations. And we can also handle symbolic input just in case we want to see which formulas we are using internally. So something like that, something very simple. So that would be the formula for the uncertainty error standard linear propagation of in a square root. And of course, if we now replace the numbers that we had inside, we obtain the same value. Right? That's very simple. That's a basic idea. So we were talking about significant figures. So this is one of these points in which there is no agreement of how many significant figures to show. So following the particle data group, which is, again, a big player in this world of uncertainty, we will follow what is called the rule of 355. This means that if we have, we look at the uncertainty. If the first three non-zero digits of the uncertainty are above 355, for example, in this case is already one more, 356, then we round to only one. So we show this as 0.4. If the error is 355, the uncertainty is 355 or less, then we show 2. We round to 2, which may be rounding up or rounding down, but we show 2. And on the upper limit, if we have 95 or more, it will be round to 1. If we have less, we will keep the 1. Right? So it's all following the same rule. So, but
for display.
This is only for display. Internally, we are keeping only these all the digits, right? And we will be doing all the computations with these digits, with all the digits we have. Right. So at the moment, the 355 is hardwired, but it will be configurable in the future. So the choice of this 355 is in order to not have too much of a change when we round in the uncertainty. So for example, going from 355 to 0.4, it's a 13% increase. If we chose, for example, a rule of 155, which is also chosen in some references, that would be a 29% increase in the uncertainty, and that's considered too much. The value can be negative, can be as small as we want, even 0, and we keep always the same rules. If this is 25, then it will have 2 digits, and therefore this needs to have the same number of digits to the right of the decimal point. Okay, that's for now. Something very important is the interaction with quantity, because this will be used a lot with quantities. So here we have quantities. Again, we can do operations, and in this case, we are having around inside quantity. So that means we have the same units for both numbers. We can have the opposite direction, in which we have around with quantities inside, and then we can have different units, right? We can do operations, and during the operations, they will be probably mixed together, so because we may not know which units we want to have. They will get mixed, so it makes no sense. You can also have mixtures of units, which are not based on base 10. So we have this kind of situation, for example, in which you have here one digit to the right of the decimal point, and here you have 2. So that's because you may have situations like this, in which you have, if you convert all to feet, then you keep 2 here, because it's consistent with 2. If you convert all to inches, you have 1 here and 1 there. So that's why at the beginning we have 2 here and 1 there. So that's the rationale. And of course, there are standard compatibility checks of units, as usual with quantities. At the moment, we are handling relative uncertainty via scale, right? So you introduce scale. This means 5% error, 5% uncertainty, and this will be converted into an absolute uncertainty. OK, so let's go to the main part of this, propagation of uncertainty. So if we have something that we recognize immediately as a numeric function, then we will do the computation and have the formula that is standard, using the standard Gaussian propagation. So these formulas, remember, are based on the interpretation of this object as if it was a distribution, a statistical distribution, just Gaussian, with mean, mu, and standard deviation, sigma. And then when you combine and do the proper statistical operation, then you get these formulas, which are a linear approximation to the exact formulas. So for an arbitrary function that we don't recognize as numeric, this doesn't do anything. And now there is here a new function, which currently we are calling a round replace, but again, it's not a very good name, so yet. It will do all the operations, saying, well, you take f of x, and then x is actually has value around mu with uncertainty sigma. And then you will get the standard formula, right? So the squares, first order derivatives, etc. Now this is all being done automatically for the standard operations, subtraction, addition, etc. So this is the case of subtraction with 2 of them. So we always have here the sum. In particular, if we subtract something from itself, we get 0. And then we have this object here with a square root of 2. We will discuss this square root of 2 more carefully in a moment. So we have products, we have division, first order division, we have powers, etc. It's all very easy, basically first order derivatives. Now, what's the difference between x plus x and 2x? Here we get different results. Where is the difference coming from? Right? Because here, so it's always 2 mu as best value, but here we have square root of 2, and here we have 2. So what is the difference? Well, here is where correlation plays a big role, and we have to be careful about it. So if we introduce here the notation for replacement when we have a multivariate case in which we have the vector of variables x1, x2, and we have the vector being mu1, mu2, best value, and each one has its own sigma. This is the case of independent statistical random variance. So we have that result. Now, this is equivalent to this case. So now here we are introducing a covariance matrix. Instead of just the diagonal, we introduce the covariance matrix. We get the same result. But now this notation allows to introduce correlation. Right? So in this case, for example, we say that the two variables are correlated. So now we have these two terms of diagonal, and we get this new result with a larger uncertainty. Right? And now, yes, so this case is where when we replace the mu's, now we get the factor 2 instead of the factor square root of 2 that we had originally, right? So this is the case in which, so the 2 means correlation. So in retrospect, what was happening here is that we were considering this x and this x, or rather this around and the other around, as independent statistical objects, right? And while in this case, it's just twice the same. So we get a 2 instead of factor of square root of 2. The case of two variables is especially important in the literature, and so it has its own notation with a correlation factor rho here, right, which has values from -1 to +1. So this is the case, and we see here how if the correlation is 0, then this is 0, then we have our square root of 2. If the rho parameter is 1, then we can have a square, a complete square, and then we have a 2 in front of sigma. So that's important of correlation. And then another way of looking at correlation is like this, which is an example I took from another standard reference, which is Taylor's book. So imagine that we have these two rules of replacement. P is going to be an uncertain variable with best value P0 and delta P as uncertainty, same for Q. And I just have this simplification function saying, well, everything is real, very simple. So this is the correct result if we do the computation. Okay. Now, can we just use replace all as usual? Well, the answer is no. If we just did replace all, we would get a completely different result. And you see, this is a sum of squares, sum of positive variables, so of positive objects. So there are more terms here which are not present here. So what's going on here? The difference is that, of course, again, we are considering that this P and this P are independent, but they are not because they are in the same formula. So if we write this expression as this other expression, in which P and Q appear only 1, then we can do the computation with replace all. And you see, we get the correct result, and not this one. So again, this is a problem of correlation. We could express, we could express the correlation like saying P1, P2, but P1 and P2 are fully correlated, and then we would get the correct result. So this is another example of how correlation is very important when we do actual computations. The GAM document gives a variety of examples just to make sure that we are all understanding what's going on, and I just took one of them, the first one. They say take these 6 variables and let's compute this formula. And you see some of them are repeated, like alpha S or theta S, etc. So they give then a bunch of information about what's the actual uncertain objects we are measuring. So we have, for example, this one. So I'm going to create a rule for each of them. Then some of them come, for example, from fitting. So we take the mean, and then the deviation of the mean is the deviation divided by the square root of the number of measurements. This is a way of adding new sources of uncertainty. This is the number coming from confidence level 3, again and again. So these are the evaluation values of the uncertain objects. As I said, we don't care about where they are coming from. We just care about how to merge them. And now, after a couple of pages in which they do a very careful, slow computation, they arrive at this result. I'm copying their final statement here, right? So we can do that with a round replace, which will take care of correlations and everything, all at the same time, and we arrive at the exact same result they give. They don't like the plus-minus notation, and they prefer to write everything in words, as here. But we still keep the plus-minus notation. OK. So that was an example. Now, how can we do better? Well, first, as I said, this is based on Gaussian propagation, linear Gaussian propagation. So a way in which we can do better is first by including higher order terms. So this is the standard formula for linear propagation, in which we only handle first-order derivatives. Now we can do better and include second-order derivatives, just in case we are working with a function in which, for example, the first-order derivative vanishes, and then we need to go to higher orders. Or for some reason, this has a especially large value, and we need to handle it. Right? So just to show you a comparison with the statistical functions, this is the equivalent of transforming a normal distribution with a square. And we can check that this result and this result are equivalent. With the statistics, we can also compute skewness and higher moments. Here we will see in a moment that we can do that as well here. The difference is that in the statistical transformations, this is all done exactly. Here we are always using Taylor expansions so that we can do more cases, but there will always be an approximation to a given order. This is exact because we are using a polynomial. Yes, so this is showing that if we add 0 here, it means, well, we are worrying about the skewness as well. Right? This was the mean, this was the variance or standard deviation, and this is now the third argument allow you to express skewness in your original distribution for the measurements. Okay, now we can go to higher orders as well, including skewness, and this will be the formula. And you can go up to order 4. I have hardwired all the formulas up to order 4, including correlation. This is an example that Professor Hanson suggested yesterday, which is let's do division with 2 variables, and let's have correlation and do it to second order, right? And that would be the result. And for example, the GAM document, in the examples we did, they say here, well, what we did is fine, but actually there are some terms that are important at second order, so let's do them as well. And then they have many more computations here, right? So with around replace, we can just put a 2 here, and the result, which they say, well, the result changes from 32 to 34 nanometers. Well, we just guessed here, the 34, just by changing here to 2. Very quickly, we can handle an asymmetric uncertainty. So we have plus value different from the minus value. This is the left one, this is the right one. And we can do computations again, as usual. And what's going on here basically is that we are doing separate computations for the left-hand side and the right-hand side of the interval. And this show how we can have 0.4 on the left, 0.7 on the right, and that explains these 2 different values here, the 1.6, the 2.8. Then some of the visualization functions have been already extended to handle around. So, and here you see we have this generating random values of around, and so we can have something like that, or list line plot will join those values, or bar chart, etc. Right? Very nice. Okay, and in my last minute, I will just talk about new things that we want to do here. So we need a native understanding of coverage factors, like when you say 3 sigma, or confidence levels, when you say 95% confidence level. So we need a way of expressing that directly inside a round, and it will know what to do. We need to see how to treat complex numbers and the fact that typically the real and imaginary parts are correlated, because you do operations and they rotate in complex space, and so they get correlated. We also want to extend this to dates in the same way that it interfaces now with quantities. We want it to interface with dates, so we can talk about dates which are kind of fuzzy, not fully specified. And of course, this needs to be propagated through the system and parts of the system that worry about uncertainty, like fitting functionality, etc. As I said, if you have criticisms, comments, or suggestions about more things that this should do, places you want to use it, or suggestions for names, please let us know. Thank you.